The last few months, I've been working on my own open source version of Perplexity. I call this project Jared. Jared is built with LangGraph and uses several techniques like Retrieval-Augmented Generation, meta prompting, chain of reasoning, and also web search to be able to do long-running research tasks. Jared works locally and works with open source models as well as some of the major proprietary model providers such as Claude 3.5. In this video, I'm going to be doing a technical deep dive on how Jared works. You'll get to see the inner workings of the agent, and you also get an explanation from me about the architectural choices and the specific choices of technology that I have used to develop Jared. Jared is open source, and I have linked the GitHub repo in the description to this video. So I'll be doing a short demo of Jared to show you the capabilities of the agent as it is now. If you have seen my previous videos on Jared, this one will be slightly different because I have made some amendments to Jared since releasing those previous videos. Not previously gone on a deep dive on how Jared works, so you'll want to stick around if you're interested in that. At the end of the video, I'll be giving you my insights into where I think Jared could go in the future, how it could be adapted for other purposes, and also some of the improvements I'd like to make to Jared in the short to medium term. I'm open sourcing Jared, and I'm doing these videos to get your feedback from the community, so to inspire discussions on actually how to build an open source agent that can be competitive with the likes of Perplexity for long-running research tasks. I acknowledge right now that Jared is far from perfect, but by open sourcing the project and getting your feedback, I believe that we can iteratively improve. I've also recently applied to the GitHub sponsorship program. So if you're interested in sponsoring the development of Jared, you'll be able to do that as soon as the application gets processed. I'll link that either in the description to this video or in the comments as soon as it's available. Okay, let's get into the technical details. Let's peek under the hood of how Jared works. I think a good starting place is to look at the Jared architecture. So what you can see up on screen now is a schematic diagram describing the Jared architecture. It is fairly complex, and there are some complex concepts that I will need to explore. So what I'm going to do is I'm going to walk you through the architecture using an example, and then we'll explore some of the code behind components of the architecture. And then I'll walk you through a demo where I'll show you how Jared works live with this architecture in place. And hopefully by the end of it, it's going to solidify all of those concepts, and you should have a clear picture of how Jared works, hopefully. Let's start with understanding what the purpose of Jared is in its current form. It's a research assistant, so it helps you to perform tasks that require research from the internet. All right, so it is similar to Perplexity, but there are certain differences, and these will become obvious as I talk through the architecture, and it will become obvious as I demo Jared to you. So let's first have a look at the first component of the architecture, which is the requirements gathering process. And I'm going to zoom in here so you can get a better look of what's going on. So the best way to understand Jared, as I said, is to take a hypothetical question or a hypothetical research task that we might have. So one I've done in previous videos, but I think it will help to talk through here with you, is the task of sourcing products. So let's say we're a restaurant and we want to source cheap Wagyu beef. We start interacting with Jared on the front end, and we enter this requirements gathering process. So at the start of this process, Jared introduces itself as an agent that is there to assist you with refining your requirements towards a goal, and then that goal can be passed on to an agent team to be processed down the line. So as you start this requirements gathering process, what's going to happen is Jared will prompt you for your headline goal. So what do you want to achieve? In our case, we're trying to source cheap Wagyu beef. As we enter this requirements loop, what happens is Jared will take your goal and will ask you follow-up questions to help you refine that goal. So this will continue iteratively to build out a detailed set of requirements that we can pass on to subsequent agents, which I will come on to in a moment. So that's the key thing here. This is an iterative process that Jared does with you by asking you questions, asking you follow-up questions, and Jared will work to compile your requirements until we decide that the requirements are adequate. And the way we decide requirements are adequate is by telling Jared. So within the Jared application, if you type /end, That notifies Jared that the requirements gathering process should come to an end, and those requirements are solidified and sent down to the remainder of the agents to process and deliver on your objective. Okay, so what's different about Jared to the likes of ChatGPT or Perplexity is that process of requirements gathering and creating follow-up questions based on your initial requirements and building those detailed set of requirements out. Jared kind of handholds you through that by asking questions to help you flesh out those requirements in more detail. That's what's different between Jared and the likes of Perplexity and also the likes of ChatGPT or even Claude 3.5, the chatbot apps that you probably interacted with. Once we have our detailed set of requirements, we pass those on to the meta expert. The meta expert is really the central component of Jared. There are a few complex concepts here. The first one is chain of reasoning. And the second one is meta prompting. Now, these two concepts are what I call prompt engineering techniques that help the meta expert be a really flexible research assistant. That's the key thing to bear in mind here. Meta prompting at a high level is where we get the meta expert to write prompts for agents down the line. So agents downstream for the meta expert, we're not writing the prompts for those agents. The meta expert is doing that. It's writing prompts for those agents. Chain of reasoning is a prompting technique that I have used to enable the meta expert to plan and think through the steps that it needs to take to achieve the high-level goals set out in our requirements. I know that was a mouthful. I know it was pretty wordy. And, so far, it might seem complex to put all of these things together. But if you stay with me, I promise you, as I walk through the code and as I walk through the prompts and finally demo Jared to you, showing you how everything works on the back end, this stuff will all become crystal clear. So bear with me. So we have the meta expert that uses two techniques, chain of reasoning and meta prompting, in order to be really flexible in helping us achieve our goal set out in the requirements that was passed on from the initial requirements gathering process. The meta expert has access to two types of agents, which we'll call experts. It has access to an expert that has tools. In this case, the tool is the internet. So we're able to perform research on the internet using search engines. And it has access to agents that don't have any tools. So in this case, our non-tool experts are a writer. So any type of generic written task that we need to do, whether it's writing a joke or even writing a short story or writing a newsletter, and a planner. And the idea behind the planner is to, based on the requirements, come up with a plan to address requirements that might be more complex. So the meta expert takes in those requirements. Based on those requirements, it decides which one of these types of experts that it needs. So whether it needs the tool expert, which in this case is an expert internet researcher, or whether it needs the expert whether it needs one of the experts that doesn't have access to any tools, so a writer or a planner. And the way it decides this is by using its chain of reasoning. And, as we start walking through the prompts, you'll get a better understanding of what this chain of reasoning is doing. So the meta expert will come up with a prompts for either the tool expert, so the expert that's going to research the internet, or one of these two experts, the writer or the planner. So it will say something like, if it's going for the planner, it will say, can you come up with a plan to find cheap Wagyu beef in Australia, for example? And the planner will come up with that plan and feed that back to the meta expert. And that plan will be there for the meta expert to then decide the next steps they need to take to achieve the overall requirements. If we don't need a plan, the meta expert can go for that same use case and say, okay, we need to find cheap Wagyu beef. Can we go on Google Shopping and find that Wagyu beef? What's the cheapest we can find? And we'll direct that over to the internet researcher that will go and execute that based on the prompts. The router is how we are routing to the different types of experts here. So we have a tool expert and a non-tool expert, and also a final output. So I'll come on to the final output in just a moment. But what you should understand about a router is based on what the meta expert says, or based on what the meta expert generates, we are going to route to 3 different paths. We'll either route to the tool expert if we need to do internet research. We'll route to the non-tool expert if we need to do planning or writing. And we will route to the final output if the meta expert decides that it's done enough research and got enough information to actually deliver a final output to the user. So that's what a router does, and that's powered by a large language model. As if it wasn't obvious, all of these steps are powered by large language models. So the meta expert is a large language model, the tool expert is a large language model, and the non-tool expert too, the router, of course, and the requirements gathering is also done by a large language model. That's it for the architecture. Everything here is strung together using LangGraph, and there's a few reasons I like to use LangGraph. I have done a previous video on LangGraph. It is a complex, I would say it's a fairly complex framework, but if you can get over the complexity, it is incredibly versatile. It's one of the most versatile frameworks that I've used for building agents, especially if you want a high degree of customizability. So LangGraph is one to look to. But yeah, precisely the reason I've used LangGraph is because it enables me to build a complex workflow like this one. And I've been able to tweak it and improve it and slowly get to the point where the workflow is getting more reliable. All right. So it's not perfect. It is far from perfect, but when I believe I'm moving in the right direction, use it by iterating, and LangGraph has set me up well to move in the right direction in terms of flexibility in building this workflow. So all of these agents are strung together with LangGraph. Okay, that's it for the architecture. There is a lot more detail to explore in each of these components. So what I'm going to do is I'm going to talk next a bit about the prompt engineering. I'm going to bring up some prompts on screen. I'll bring up the requirements gathering prompt and the meta expert prompt, because those are the 2 major prompts that really make Jared work. There are other prompts that exist within the other experts. So there's prompts that exist within the tool using expert. Once we get onto the Python code, you'll see how those prompts work within the tool using experts. So just hold fire for now. We'll move on to the major prompts, which are the requirements gathering prompt and the meta expert prompt. And hopefully that should start to build the picture of how Jared is working behind the scenes. What I have here in front of me now is the prompt for the requirements gathering part of the Jared agent. Now, it's not worth me reading through every single word of this prompt, because you'll have the prompt for yourself. It's available to you in the GitHub repo. But Jared, you can take a read of that in detail in your own time. But I want to explain to you the high-level concept that really makes this requirements gathering work. So the requirements gathering does use, I failed to mention this when I was talking about the architecture, but even in the requirements gathering, we use a variation of chain of reasoning. And what I've set out here is something I call chain of goal-oriented reasoning. Chain of reasoning is something I borrowed from a project called Professor Synapse. I'll link to it in the description to this video. So definitely check that project out when you do have a chance to. It's a good project. Chain of goal-oriented reasoning is centered around this dictionary that you see on screen. And I'm going to zoom in to give you a better look at that dictionary. With chain of goal-oriented reasoning, I'm essentially asking the Jared requirements gathering agent to, first of all, keep track of the primary goal, generate a list of requirements, add user preferences, and Jared will infer some of those user preferences if they're not given, make adjustments to fine-tune the response or the requirements, and then put in place a step-by-step strategy to actually achieve that goal. The key thing here is this Kogo chain of goal-oriented reasoning is generated before Jared asks any questions. So essentially, you have this Kogor generated, and then Jared asks questions based on that generated Kogor to enable you to refine your requirements. The questions take a few forms, and I'll get down to the forms of those questions. So there's 3 types of questions. There's a goal clarification question. There's question to explore the requirements set out in the Kogor. And then there's also goal alignment questions. So those are 3 types of questions that Jared will ask when you're interacting with the requirements gathering agent. Now, there's a trick here to understanding why it's important to put out this Kogor. So when I say Kogor, I'm obviously talking about this dictionary. And it's the same thing that applies when we visit the prompts for the meta expert as well. So bear this in mind. What you should remember about large language models is that they are auto-regressive. This means when a token is generated, that token is actually fed back into the model and used as a basis to generate the next token. So we generate our first token, that's fed back into the model, and that's used as a basis to generate the next token. Those 2 tokens are fed back, and they're used as a basis to generate the 3rd token, and so on. It's auto-regressive. So tokens that have been generated previously will influence the tokens that are generated next. And that's why you can use techniques like this. Another technique that's similar to this is chain of thought, where you ask the large language model to output its thought process before giving an answer. And it's been shown in research papers to improve the performance of models. But essentially, you can use techniques like this to improve the performance and the output of models, because you're asking it to generate its own context before asking those questions. So by asking it to generate the Kogor, I'm asking the model to list out the goal, keep track of the requirements, the preferences, any adjustments, and also any strategy, and then ask the questions. So those questions are going to be more relevant to the goal. That's the philosophy behind it. That's the thinking behind taking this approach. And you'll see how this works in practice when I start demonstrating Jared to you from a back-end perspective. You'll see this actually update live in real time. Now it's time to explore the prompt for the meta expert. So this is what I have on screen currently. This is a lengthy prompt. It's almost 2,000 words. And I'll say right off the bat that this prompt does require a lot of optimization. I believe it could be made shorter. If you're looking to contribute to Jared, maybe that's something you could work on. Could definitely be made shorter to be more token efficient. And some of the language in this prompt could be more precise too. But I'd like to talk you through the principles or the philosophy behind this prompt. And we're using 2 techniques. We're using the chain of reasoning, and we're using meta prompting. We covered a variation of chain of reasoning in the last requirements gathering prompt. So I'm going to start with the meta prompting, because really this thing is built around meta prompting, and then I'm going to zoom back out and show you how that integrates with chain of reasoning. I will read the persona on this one, and I'll read a bit of the objective. You are Meta Agent, a super intelligent AI with the ability to collaborate with multiple experts to tackle any task and solve complex problems. You have access to various tools through your experts. Okay, so that's the persona of the prompt of the agent. The objective. Your objective is to collaborate with your team of experts to produce work based on a comprehensive set of requirements you will receive. And these requirements will be available to the meta expert within these tags, so within these requirements tags. I'm going to come back to this chain of reasoning, but I want you to follow me through to the meta prompting so I can explain to you how this works. So how I've outlined this in the prompt is by talking about achieving objectives. So I said, as meta agent, you are constrained to producing only two types of work. Type 1 works are instructions you deliver for your experts. Type 2 works are final responses to the user query. Okay? So there's two types of work. There's type 1 work, which are instructions we deliver for the expert. And there's type 2 work, which is a final response to the user query. Okay? So let's look at what type 1 work actually looks like. One trick I use here is I give examples. So I give an example of what type 1 work might actually look like. So let's talk through the type 1 work. So first, generate the chain of reasoning to think through your approach. So recall when I was talking about the requirements gathering, I was saying we generate the chain of goal-oriented reasoning first, and then we generate the questions. So with the meta expert, we generate the chain of reasoning first, and then we produce the type 1 or type 2 work. So first, generate the chain of reasoning to think through your approach, then produce type 1 works when you need the assistance of an expert. To communicate with an expert, type the expert's name followed by a colon. Then provide detailed instructions within triple quotes. And here we go. Here's an example of type 1 work. So we have our chain of reasoning. So this was what we want meta expert to produce. We have our goal. And remember, that goal is sifted out through the requirements that we pass on to the meta expert from the first requirements gathering step. So our chain of reasoning here has various aspects to it. So this is a research agent. So we have a summary of the internet research that's been conducted up till this point, a shopping list summary. So the agent, through the tool agent, has access to Google Shopping and Google Search. So we have a shopping list summary, and that's for tasks like sourcing Wagyu beef, as I showed before. A plan. So remember, the meta expert can ask for a plan. When that plan is generated, we ask the plan to be put into this field here. So the plan generated by our expert planner is actually then recycled and put into this field. So it's available to the meta expert through the chain of reasoning. The progress measures the progress towards the goal. There's a flag here that signals to the expert that it's time to produce type 2 work, and we'll get on to what type 2 work is. We have the user preferences outlined, and this will be taken from the requirements. We have adjustments. Any adjustments that the meta expert decides we need to make down the line are here too. We have a strategy, and the strategy is helping us move in the direction of this goal. Now, arguably, we don't necessarily need both the plan and the strategy. So that's a point of optimization here. Maybe we could get rid of the strategy because essentially the plan should be a strategy anyway. We have expertise. So we're stating the expertise that we require to meet the goal, and that will obviously change based on the strategy and the plan. Then we have some controls here. So planning here means based on the goal and based on the requirements, do we need a plan? So some tasks don't need a plan. They're simple tasks, right? So in this example of just find the current weather in London, we don't need a plan. It's a simple task. Here's another thing. Here's another control. Do we need internet research? So the internet research is required here because we need to find the current weather forecast. So that's why we state here, internet research is required to get up-to-date weather information. Shopping. Do we need a shopping list? For a weather forecast, we don't need a shopping list. So these controls help the agent to understand what expert is needed next to meet or to move towards completing that goal at the current step it is in the agent workflow. Once the meta agent outputs this chain of reasoning, it will then follow on to output either type 1 or type 2 work. So in this case, we're looking at type 1 work. So our type 1 work in this case is the expert internet researcher, because we need to find the weather forecast. Remember, our goal here is find the current weather conditions in London. That's our goal here, high level. Find the current weather conditions in London. So therefore, with this as the context, it serves the meta expert. It allows the meta expert to be in a better position to then direct the workflow to the right expert to help meet this criteria. So this is almost like the thought process. We're asking it to think out what's already happened, essentially, what we need, and then tell us what expert we want. So in this case, it's the expert internet researcher. And then we ask the meta expert to come up with a prompt for that expert internet researcher. And if you recall our flowchart, that will be fed to the tool using agent, because the internet is a tool that we need to actually perform this task. So that's the type of type 1 work that we would deliver, expert internet researcher. Now, for type 2 work, what we do is, again, we use the chain of reasoning to think through the approach. And then there's some rules for producing type 2 works. So naturally, what you would really want is for the agent, the meta expert, to be able to decide on its own when enough is enough, when it's gathered enough information to produce the type 2 work. Now, this doesn't always work out. Sometimes the agents are not intelligent enough. The large language models, the current generation we have, aren't intelligent enough with some problems to understand when they've gathered enough information. So there's a fail-safe in here that I've put in place that says when you are explicitly instructed to deliver type 2 works, if you do not have sufficient information to answer it for, you should provide type 2 work anyway and explain what information is missing. Right? So we're saying you either produce type 2 work when you've gathered sufficient information from the experts to respond to the query in full, or when you are explicitly instructed to deliver type 2 work. And if you don't have the information at a point you're explicitly instructed to deliver the type 2 work, you should deliver it anyway and just explain what's missing. I have a mechanism in there, and this is in the Python code. There's a mechanism in place that when we reach the maximum allowable number of iterations for the Jared workflow, there's a message that is injected into the prompt to say, you must deliver your type 2 work now. It works, I would say, 70% of the time. Sometimes the agent does overrun and doesn't produce type 2 work in time. So I've added a little bit of a buffer in there to catch those scenarios. And I think that gets it up to about 80% of the time. 80 to 90% of the time. So yeah, there is room for optimization. And also that number is higher and lower depending on the models you choose. I found that Claude 3.5, although it works really well as an agent, sometimes it can get confused about when to produce type 2 work. It seems to work okay with GPT-4 Omni. And even with the mini version 2, it seems to work all right. It seems to produce type 2 work on the first time of asking. Okay. So this is what type 2 work looks like. So we have our chain of reasoning. And you'll notice here, if you look at the goal remains the same. But look what's in the internet research. So this, by the time we produce our type 2 work, we would have gathered some information from the internet, and it will be here reflected in the chain of reasoning. Notice the shopping list summary is blank. We don't need a shopping list for this task of finding the weather. Plan is blank 2. The progress is 1. We have the flag, produce type 2 work, which is now marked as true. There's some user preferences here. There's a strategy here. And then there's the expertise here, expertise in weather reporting. Okay. Planning, we have all of the information we need, and we are ready to deliver a final response. No plan is required. No internet research required. We have all the information we need. So these are the controls. Shopping, we are ready to deliver a final answer. No shopping list required. And then we deliver our final answer, and the final answer takes this form. There's double arrows here. Final answer, and then you can see current weather conditions, and we deliver the final answer with the sources. So this is an example to show the meta expert how we should go about delivering type 2 work. And the previous example was how we should go about delivering type 1 work. Then there's a bit of information about the experts themselves. So there's information about the expert, internet research, and its capabilities. So we mentioned, we have access to Google search engine. So we have access to both the shopping and both search and shopping tasks via Google search engine. We have some rules about working with the expert internet researcher. The same with the planner. We talk about the capabilities, working with the planner, and same with the writer. Okay. We talk about how the expert work is delivered. So this is key because it provides a good separation for the model for the large language model power and the meta expert to understand what piece of information is what. So the expert plan is within these tags. Expert writing will be within these tags. Any expert internet research, any expert research or shopping list will be within these tags, the internet research shopping list. Any expert internet research will be within the internet research tags. So the large language model has a clear idea of where these things are. And then we have some best practices of working with experts and important reminders. There is a lot there. I would advise you to go and read this for yourself in the GitHub repo, but that's essentially how the prompt works for the meta expert. If you join me in the next section, I'm going to do a whistle-stop tour of the code. The code base is pretty extensive, so I can't cover all of it here, but I'll cover the important parts of the code. So I'll cover where the agentic workflow is, and I'll talk about, with a particular focus on the tool expert, because there's a lot there that we need to cover. And that will go on to talking about how we're using the tool expert for internet research and how RAG plays an important part in that too. So stay tuned for that. It's time to have a look at the Python code behind Jared. Now, the code is available to you in the GitHub repo that is linked to the description in this video. So please feel free to open that code up, walk along with me, and check it out in your own time. I will warn ahead of time that the code base is fairly large. We're talking about thousands of lines of code in here, potentially. I'm not, therefore, going to have time to run through every single detail of the code. Instead, what I'm going to do is I'm going to pick out some of the most important concepts and scripts within this code and talk through a little bit about why I've put them together in the way they are. And also, I'll point out areas where there is room for optimization within this code. All right, let's start at a high level. The project takes a fairly simple form. If you would direct your attention to the left-hand side of the screen on the menu, what you can see in the project, which is now called Meta Expert, but I might change the header project to Jared. There are several different folders here. Agents, that contains all of the agents that work in this folder. So Jared agent is the main one. That's the one that has the front-end interface. I have had several iterations of this. So Meta agent was the first iteration. Then I had a Jared agent that just operated in the terminal. And Then the Jared A underscore agent. So apologies, Jared.py was an agent that just operated in the terminal. The Jared underscore agent is the latest iteration of the agent, and that has a front end associated with it. So this is the one that you want to be looking at if you're either taking this repository for yourself or you want to use it. You should be looking at the Jared underscore agent.py. The base agent is just an abstract class that helps me write agents that slot into this framework a lot easier. So that's all that is. That's what the base agent is. It's an abstract class. So we have agents. We have the documentation. We have the configs, and configs is where you will enter the configurations for API keys that you need to get this up and running. Docs, this is where you have all of your documentation for Jared, and I'll be updating this as I add features to Jared too. So keep an eye on docs. We have models. Models is where I have implemented all of the API calls I need to make to the various model services. So Jared is compatible with Grok, Mistral, OpenAI, Claude. It's also compatible with VLLM, which is an open source inference server, which means you can stand up your own large language models on either your own GPUs, or you can rent a GPU and stand it up on there. And the VLLM inference server mimics the OpenAI server. So Jared is compatible with that too, if you've used VLLM in the past. I have a video that I've done previously on Jared showing you how to get set up with VLLM. And it's also compatible with Ollama. So I haven't done any rigorous testing with Ollama, but the integration is there. I've been struggling to get Jared working with Gemini. So it's not compatible with Gemini for the time being, but I will be looking to build that compatibility in. So that's in the models folder, and you can find that by visiting llms.py. And then prompt engineering, this is where we keep the prompts for Jared. We've already gone through the major prompts, so you can explore this yourself by looking into the prompt engineering folder. Tools. Tools is another important folder, and this is where we keep things like the Google search tool. So that's Google_serper.py, and the offline RAG tool. And the offline RAG tool is a really important tool for actually making Jared be able to pull relevant context from the web pages that we find on the internet. So that's all in the tools folder. And then the main interface for Jared is the chat.py. And the chat.py leverages a library called Chainlit, which is an easy to use front end for chat and agent-based applications. That's an overview of the Jared folder structure. Now let's explore some of the most important scripts, and we'll start off with the Jared_agent.py script. So this is the one I have open currently. I'm going to zoom in a little bit to give you a better view of the script. So this script is quite long. I think it's above 500 lines of code. But essentially what we have here is we are defining all of the agents that I showed you in the Jared workflow schema. So right towards the start of this video, I showed the diagram of Jared working with the requirements gathering and the meta agents, the meta expert, and then the other experts like the ones that require tools and the ones that don't require tools. So we define all of those agents within this Jared_agent.py script. You can have a look for yourself and see how we do that. So there's a lot of utility functions there at the top, but let's go straight into how we're defining the agents. Every agent in Jared is based off this base agent. So I said this is an abstract class. It just allows me to create agents that slot into this Jared. I don't want to call it a framework because it's not really a framework, but that slot into this Jared workflow conveniently. That's all. They share the same methods, and you can make adaptations of those methods to suit that particular agent. So you'll notice a pattern here. Every agent has the same methods defined, but slightly different depending on the purpose of that agent. So the first agent we have is Jared, and that is the requirements gathering agent. So you can see here where we get the prompt, we're taking the requirements gathering prompt. This is another tip as well that I would like to drop. All the prompts I write, the big ones, I write in Markdown now. And you might have noticed even when I was going through the prompt, it was rendered quite nicely in Markdown. So I use Obsidian. I write my prompts in Obsidian. There's two reasons for that. The first reason is it's easy for me to understand what's going on because it renders very nicely. And the second reason for that is much of the internet is written in Markdown. And it turns out that large language models are quite good at interpreting prompts in Markdown. And Markdown gives you the opportunity to express things within your prompts that would be much more difficult to express via just plain text. So that's Jared. This is the prompt. Then we have something to process the response and update our state. And I'll go back to talking about states because this is a key part of how LangGraph works with agents. We can get our conversation history. If we want, we can get a user input. Guided JSON, this is when we're using our own inference server. We need a guided JSON to help Jared return JSON responses when we need to, but in this case, we don't. And then we have the run method. So for the Jared agent, for the requirements gathering agent, so here, Jared agent is the requirements gathering agent. We're actually running this directly in the chainlit front end. So that back and forth requirements gathering happens in the chainlit front end. So this is what this method helps us to do. We then go on to define the meta expert, and you'll notice we have very similar methods again. It's all based on the same abstract class. So we're getting the prompt. And this time we're getting the Jared meta prompt. That's the prompt we're working with. We're processing the response. So here, when we process the response, we're updating a different part of the state, and I'll get onto that state when I show you these agents. When I finish going through the rest of the agents, we can get a conversation history. The different aspects of our conversation history that we want to pull, we can use this method to get them. You can see this one differs from the last Jared agent. So this is the meta expert. You can see how here what we actually want to retrieve in our conversation history is the plan, expert plan. So we can get that. We can get any expert writing that we've done. We can get any expert research for shopping, and we can get any expert internet research too. So that's how we can leverage this method to pull the history. And then the other methods here, getting a user input. So in this case, we're not actually using this user input, but if we wanted to get a user input, we could do it by updating this get user input method. And then we go on to the run method. And the run method is putting everything together and running this agent. So we're running the meta expert, which will deliver our chain of reasoning and then the instructions to the other experts downfield, or a final response, and it will update the state too. So you can see where that happens. So I'm not going to go into all of this in detail. There's quite a lot of formatting things here and some boilerplate, but you can have a look at this yourself in your own time and understand how it works. Then we have the no tool expert. And again, you'll recognize similar methods stood up. So we're getting the prompt. This time the prompt notice is coming from the prompt that the meta expert created. So this is the meta prompt, because remember, the meta expert is the one that prompts our no tool agent and our tool using agent. So we get the prompts not from a markdown, but from something the meta expert generated. We have a way of processing the response. You can see that there. And then we can run the agent and put everything together. So have a look at that in your own time. Now, the tool expert is a little more involved because we do require the use of tools. So I am going to go into both the tool scripts to show you what they're doing. But let's take a look at the tool expert first. So we have the tool expert. We're getting the prompt, and notice again, this is the prompt from the meta expert. This is what we're pulling in as our system prompt. We're processing our responses. And here's where the tool expert is a bit different. There's some additional methods here because we need to use those to be able to leverage our tools properly. So we have two tools primarily that the meta expert uses. a search engine tool, which can either be just a pure Google search or a search on the Google Shopping API, and an offline RAG tool. So it's offline because it runs 100% locally. So there is actually a prompt here to help with generating search queries. So this prompt outlines an algorithm that is used by a large language model within this tool expert that allows for search and exploration in a search engine. So we can decide a number of queries that we want to run, or a number of queries that we want to generate, and we get manager instructions, which is just really the meta prompt. And based on those, we will deliver a set of queries for some particular goal or some level of internet research that we want to do. If this isn't clear right now, when I demo a run through, when I show you a run through of Jared, it will become clear because all of this stuff is going to be outputted into the screen. So you'll see that on the log and you'll see exactly what we're doing here. But this is part of the tool expert. So this is part of the tool using agent. And then we have another thing to process our search engine results page, our SERPA result. So what we want to do is, based on the search engine results page that we return, we actually want to select which is the best URL to answer our search query. So that's what we have here. We have our search query, we have our search engine result, and we want to pick the best URL to answer that search query. So this is what this is doing, and this is also done by a large language model. You might notice this as a prompt. So we've got two stages. We've got a first stage where we do multiple searches in parallel, and we can decide the number of searches that we want to make. And it follows that search algorithm. So I would implore you to read this search algorithm yourself. It's very basic, but it's supposed to be general. There's probably room for optimization here. So that's the first stage. And then the second stage is, once we've returned the search engine results page for all of those searches, the large language model will pick the best URL from all of those parallel search engine results and just compile a list of the best URLs from all of them. So if we do 4 parallel searches, we'll end up with 4 URLs because we take the top URL from each search engine results page that's run that comes from our parallel searches. So then we sling everything together in the run method. So I'll show you now where the RAG component comes in. So there is something I missed in this tool using agent. So there is a use tools method. I think I skipped over this. So here we are. There's a use tools method. And what we do is, depending on what mode, so if we're in SERPA mode, we can use the search tool, or we can use the shopping tool. Otherwise, we're in RAG mode and we use the RAG tool. I'll get into a bit more detail about how the search tools and RAG tools work in a moment. So essentially, we have our list of URLs that we want to draw data from. So once we have that list of URLs we want to draw data from, and that's all done within the run method, you'll see here in a moment. I'm just finding it. Here we go. So we get our list of URLs that we want to draw data from. We process those, so we're making sure those are unique, because sometimes you can get duplicates. You don't want to waste any computational power, so we make sure those are unique URLs. And then we move on to trying our RAG tool. So what we do with our RAG tool is we take our list of unique URLs, and the RAG tool has a local document ingestion server that takes, for each URL, takes the content of that URL, uses an open source project called LLM Sherpa that sits on your host machine. That uses intelligent chunking via, I think they use a modification of the Apache Tika server. That uses intelligent chunking to break that document into chunks. Then we use an in-memory vector store face And Face creates embeddings and does similarity search. And we do that in parallel. We do that in batches once we've done the intelligent chunking. And then we run a cross encoder over that similarity search to re-rank those documents. And that is our retrieve context that gets fed back into the research for the meta agent. So this might be, this is usually for search. For shopping, we don't use RAG. For shopping, the shopping API returns a convenient summary, which gives the product and the website, the URL, and also the price. So because of that convenient summary, we don't need to do any RAG. So we just feed the entire thing back into the shopping list for the meta expert. But when we're using Google search just normally, and we want to get the content from a web page, we can use RAG to do that. Okay. So that's the tool agent. I'm going to show you both. The last agent to show you is the router. So the router, again, is fairly basic. We have some of the same methods. So we have the prompt here. Remember, this is all working off the meta agent. So the meta expert talks to all of the other agents. So we get a prompt from the meta expert. And after that, what we're asking the router to do is to decide based on the manager response, which is just the meta expert. So there's probably some naming stuff here that I could do to make this a little bit easier to understand as code, but bear with me. So this will be the response from the meta expert. And it says, you should produce this JSON. So the router decision, which is return the next agent to pass control to. So when we say next agent, we only actually have 2 agents that we can pass control to, and then 1 end state. So we have the tool expert, and the tool expert will do all of the internet research and all of that type of stuff. We have the no tool expert, which could be the planner or the writer in this case, and then we have end chat. So these are the instructions that I give to the router to make sure that it routes to one of those 3 agents. And then that is it. Those are all of the agents. So remember, there is the Jared requirements gathering agent, which we introduced at the top, the meta expert, which gives all of the instructions to the other agents downstream. And then we have a tool agent and a non-tool using agent and a router. All right. In the GitHub repo, in the docs folder, there is an introduction to Jared document. And that gives you the flowchart that I was showing you earlier, showing how Jared works from a schematic perspective, the schematic diagram, sorry. And it gives you some explanation of the concepts I've covered in this code walkthrough for the Jared _agent.py. So have a read of that if you want to get a better understanding of how all of this works. Right, so before I show you how we string all of these agents together, I'd like to direct your attention to the Google Serper tool. And then I'd like to direct your attention to the offline RAG tool. So let's have a look at the Google Serper tool first. So it's fairly basic. What we're doing, if we ignore all these helper functions, what we're doing essentially is we're making an API call to the Serper deb. So we have one endpoint for search, and we have another endpoint for shopping. So these two pretty much mimic each other, except one is for search and the other one is for shopping. That's all we're doing. We're making an API call to those endpoints. Everything else around here is just to handle errors. And that's all we're doing here. So I understand if you're not familiar with Python, this could look intimidating, but we're just handling errors so the application can run smoothly if for some reason we can't connect to this API endpoint. So that's the Serper dev tool. And remember what that does is we can take a query and return a search engine results page for that query. And that search engine results page will either be for normal Google search or it will be for shopping. Google Serper does also have other endpoints. So we have the Maps endpoint, for example. I think there's probably about 7 or 8 different endpoints on there. But for now, I've just included the search and the shopping endpoint. The offline RAG tool. This is the script for the offline RAG tool. So we have our intelligent chunking. So remember, the intelligent chunking is run locally. Everything here is run locally. We're using the LLM Sherpa library, which is open source. You can check that out. We've got the ingestion server hosted offline on my laptop and on yours if you're running this code locally. So that should be hosted on your laptop. So if you have set this up, if you recall that you need to run a Docker image, that Docker image is the server for the intelligent chunking. So that's why you have to run that Docker image. It's in the README for this project. So this is what that's all about. This is where we run that intelligent chunking. Funny enough, just a quick thing on this. This is called Layout PDF Reader, but actually it works with more than just PDF. So it can work with URLs, it can work with HTML. It can work with HTML, it can work with PDFs, I think it can work with Markdown. There's a bunch of things it can work with. So I got a bit confused about this, but it's just the name is a bit of a misnomer. It's actually just a general layout reader. Okay. And then we have the index and rank, and this is where we use face to do this. So you can see our embedding model that we're using. I believe this is a bi-encoder, so this is just supposed to be fast embedding. What I've noticed is that face, because it's in memory, it is pretty slow, and I'm using this on my CPU, so I'm not using any GPU resource for this. There is actually a way to use this with your GPU. It's pretty slow, and because it's pretty slow, I have batched it up to improve the latency. It's one of the suggestions that I found for research to improve the latency, run it in batches. So I batched it up, and what that does is it creates the embeddings and then does the similarity search over those embeddings. So at the end of this is what all of this is doing. So when we're saying the index and rank, this is what we're doing. And at the end of this, we return some final results. So I just want to double check here because there is one more part to this. There's a re-ranking part. And I want to make sure, apologies. So this model is for the re-ranking. I think Face uses a default model. I can't recall what that model is right now, but it uses a default model for its own embeddings and similarity search. Okay, so just bear that in mind. This is for re-ranking, and we're using fast embed for that. So these all run locally. We have our index, creating the face index, which is in memory, and ordering or doing the similarity search over that. And then once we've done that initial similarity search, we can re-rank that with the re-ranker, and this is the re-ranker we're using. So that's the offline write tool. Please feel free to dig into this code yourself. There is a lot to cover, so I can't cover everything in detail, but definitely feel free to dig into this code yourself. We just pull everything together in this run rag. Pull everything together in this run rag function. We do some things concurrently as well. So the things that don't take a lot of resource. So for example, the intelligent chunking, actually, surprisingly, you can run that concurrently. So that's what we do. Whereas when we're actually doing the index and rank, we don't run it concurrently because that indexing and ranking does take quite a lot of resource. So we run that just over the entire corpus once we've got all the results and combined them. That's the offline write tool. The last script that is important that you'll want to pay attention to is the chat.py script. So this is the front end for everything. And we're using Chainlit for the front end interface. You'll see how that interacts with everything in a second. Up here is where you can go in and change the model or service that you're using. So these are the options you have available to you: OpenAI, Mistral, Claude, Ollama, Grok, Gemini, which I will comment out because it doesn't work. So there's Gemini and VLLM. So all you need to do is when you're in the chat.py script, if you wish to use a different model, simply comment out or simply replace Claude with whichever one you want within the getAgentQuarks method. I'll say not method, within the getAgentQuarks function. So if you want to work with OpenAI, just come here and type OpenAI, and you can work with OpenAI. The recursion limit is the number of iterations that we pass through before the workflow comes to an end. So I found for relatively simple tasks, 4 to 8 is enough. For more complex tasks, you'll probably want more than that, but bear in mind that's making more calls to LLM services. So you will pay more for higher recursion limits. Remember that prompt is quite large. So you're sending the meta expert prompt is quite large. So you're sending quite a large amount of tokens for each call. Remember that. So the recursion limit is set to 8 by default. So we've got an instance of an agent here, and that's just for convenience to create an intro for Jared. So this agent's only purpose is to get the workflow starting. So that's all we're doing here. So that's what we call the Jared intro agent. So we'll move on from there. So we have the way Chainlit works is it gives you these decorators that you can define these asynchronous functions so that when you activate certain aspects of the front end, so for example, sending a message or starting up the chat, these asynchronous functions also execute. So we've got one on settings update. So for the search engine, we can search via different locations. I have set as default the US, but you can also change that to the United Kingdom or the Netherlands or Canada. I think this pretty much covers every country. I haven't included that for obvious reasons to keep things short, but if you're working on this yourself, you may want to include your own country in there if it's not already in there. So this is just to get our settings updated. And then on chat start, so as we're starting the chat itself, we have a state. The state is really important here. So this is an important concept in LangGraph. The state records all of the activity of each agent within the graph itself. So each agent is free to write to the state. And what that means is any activity that's happened in the state can be recovered by another agent downstream later on. So it's a way of preserving the history of the agent interaction. So whatever Jared does, like say we've gathered some requirements, we can simply just pick those up from the requirements gathering part of the state. Or if we want to know what the meta expert, if you want to pick up what the meta expert has done, we can pick it up from the meta prompt. We can pick up aspects of the shopping list here in the expert research shopping. We can pick up aspects of internet research and so on and so forth. So the state is a really useful concept in LangGraph. And then we're building our workflow. So I need to show you what that function looks like because the concept of a workflow is a very useful concept as well in LangGraph. And I'll show you briefly what that looks like. So when we build our workflow, what we're actually doing is we're setting up that interaction between all of the agents. So a workflow is a graph in LangGraph, as the name suggests. A graph consists of nodes. A node you can think of as a point in a workflow or an agent in a workflow. And an edge is connecting one agent to another. So agents that are connected by edges can speak to each other. So we have the first node here, which is the meta expert, and then the router, the node tool expert, the tool expert, and then we have a node to signify that we want to end this chat. We set our entry point. We enter at the meta expert. So when we've done the requirements gathering, we pass that to the meta expert. So this is the entry point for the graph. And we set the finish point, which is the end chat. And then we add our edges. So our edges show which agents can speak to each other. So the meta expert can speak to the router. I'll skip down here for a second because this is important. The router has a conditional edge based on a routing function. And that routing function, remember, from the router directs to either the tool expert, the node tool expert, or the end chat. And the tool expert can speak to the meta expert, and the node tool expert can speak to the meta expert. So these are the feedback loops here. So the meta expert speaks to the tool expert or the node tool expert via the router, or delivers an end chat, a final answer via the end chat. Okay. And then the node tool expert and the tool expert speak directly back to the meta expert. So the meta expert has an awareness of what the experts that it's working with have done. And then we have a function to run the workflow too. So how it all interacts with the chat is we have this asynchronous function here. And that function gets called every time we run a message, every time we submit a message. So when we submit a message, we're actually running this workflow. So that's the workflow that we have built with LangGraph. We're running that every time we submit a message. All right. I think that's enough for the code element of this. Like I said, the GitHub repo is available to you. So if you do need to explore this more for yourself, you should dive into that GitHub repo and start playing around with the code yourself. But hopefully this is giving you a general overview of how things work. At the end of the video, I'm going to go into a bit of detail about where the optimizations are, in my opinion, where I think we could optimize this. But next, let's do something a bit more exciting. And let's actually demo Jared. Let's see how it works. And you can see all of this stuff that I've explained in theory, in action, in practice, in the demo. Let's get on to the demo of Jared. So the first thing I'm going to do is get Jared set up. I'll do this by directing myself to the root folder of the project. And then I'm going to activate the virtual environment for Jared. So I'll do that by running conda activate lab env. So your virtual environment obviously might be called something different, but I've just called mine lab. So lab env. So I'm going to activate that. So you know the virtual environment is activated once you see it here appear where base was before. That's if you're using Anaconda PowerShell. And then I'm going to get started with Jared by running chainlit run chat.py. And that's going to pull up the chainlit front end, which is a locally hosted web application. That will just take a moment to do. While that's pulling up, for this demo, I just want to explain that I'll be using Claude 3.5 Sonnet. I found that it's one of the best models to use with Jared in its current form. It does also work with Ollama, so you can use it with local models. I have tested it previously with the Llama 3.1 70 billion quantized model, and I managed to get some decent results there. But ultimately, I found the best models to use are the GPT-4o and Claude 3.5 Sonnet. And there's no surprises there. You've seen the complexity of the prompts behind the scenes. So it does require the most capable LLMs to work effectively. And you can see there where we've made the API call to Anthropic as the Jared agent has started up to give us that intro message. So I'm going to pull the web agent on screen now so you can see what that looks like for yourself. I'll close this. So there's a pop-up message from Jared here, which is the intro message. I'll expand that in a moment. Before we do that, I'd like to show you how you can play around with the Jared settings yourself. So on the left-hand side, there's a sidebar. And if you open that, you can direct yourself to the README. The README gives you the introduction to Jared page. So there's all the explanations there of how Jared works behind the scenes. So a lot of the things I've covered in this video are written out here. The only thing that's missing from this is the architecture, because the architecture isn't rendered in this format for some reason, but that is in the docs for the introduction to Jared if you do want to see that architecture again. We'll close that. Also, for those of you that don't like to work in dark mode, you can change that in the settings. So you can toggle that to light mode or dark mode. Close the sidebar. So let's expand the Jared message to give you a better idea of what this is all about. So if you remember back to the architectural diagram, the first aspect of Jared is requirements gathering. Jared provides us with a message introducing itself. I'm going to read this out for you. It says, "Hello, I'm Jared from BrainCube. By the way, quick note, BrainCube is my AI development consultancy. We build AI applications, agents, and automations for businesses. So if you're seeking to do any of that, there's a link in the description to this video for you to book a discovery call, and you can catch up with me over that discovery call to discuss any artificial intelligence or agents you want to build into your business. So please do feel free to reach out if that is what you're seeking." So moving on, it says, "Hello, I'm Jared from BrainCube. I use the chain of goal-oriented reasoning to help you refine your goals and gather aligned requirements. If at any point I stop using my chain of goal-oriented reasoning, add COGOL to your next prompt, and I will usually start again." Then it says, "Tell me, friend, what's your primary goal you're aiming to accomplish?" And then there's some clarifying questions it asks here. So we have the COGOL rendered first, or I said rendered, but generated first, and then we have this intro message. And notice here the COGOL, the chain of goal-oriented reasoning, is pretty empty. By the time we finish this requirements gathering process, we'll have all of our requirements outlined here in this COGOL. All right. And then the other thing to notice is where we're conducting internet searches from. So right now, Jared is conducting internet searches from the United States. I'm going to change that because I'm based in the UK. I want to conduct my internet searches from the United Kingdom. So the way I do that is navigating to the settings panel, and then I can select the United Kingdom and confirm. So now all searches are going to be conducted from the United Kingdom. All right, let's begin the requirements gathering process. And for this, I think it's useful to have a decent use case that many of you will be probably familiar with if you've been working in the AI space. We're going to try and use Jared to help us source some cheap NVIDIA GPUs. So I'm going to start off like this. I need to source cheap NVIDIA GPUs to run large language models. So I'm going to state that as my primary goal. Then Jared is going to take that in. And if you remember, we're in the requirements gathering process. So Jared is going to ask me some clarifying questions. It says, thank you for sharing your goal. Sourcing cheap NVIDIA GPUs for running LLMs is an interesting challenge. Let's dive deeper into this and ensure we capture all of the necessary requirements. First, we need to understand more about your specific LLM needs and the GPU specifications that would best suit them. Then we can explore cost-effective sourcing strategies. So can you provide more details about the specific LLMs you plan to run and their computational requirements? Have you considered any particular NVIDIA GPU models or series that you think might be suitable for your needs? What's your budget range for this project, and how do you define cheap in this context? All right, so let's answer all of these questions. So I want to run state-of-the-art models. For that, I have very stringent requirements for the GPU. Right, so to run the state-of-the-art models, we need GPUs that are CUDA capable. And I think right now we want CUDA 12.4 version and above. And I think for the Llama 3.1 models and some of the latest models that come out, you need CUDA version 12.4, I believe. So let's say I need the GPUs to be CUDA capable. One, it must be compatible with CUDA version 12.4 and above. 2. And in terms of memory, what I'm seeking is around 48 gigabytes of memory, because if I need to string multiple GPUs together, I can. And I think that's going to be within my budget range. So, and I require each GPU to have at least 48 of memory. Okay, so those are my requirements. Have you considered any particular NVIDIA GPU models or series that you think might be suitable for your needs? So I'm open. I'm open to any models that meet these requirements. Okay, so I'm open to any models that meet those requirements. Have you considered any particular NVIDIA GPU models or series that you think might be suitable for your needs? So I just repeated that question, apologies. What's your budget range for this project, and how do you define cheap in this context? So I am going to set a budget range. I'll set something like my budget is, let's say, 5K, so £5,000 per GPU. I know that is probably going to be tight, but it'll be interesting to see what it comes back with anyway. So let's just say my budget is 5K per GPU, right? So I've set some very stringent requirements here. I've also provided a budget range. So as before, Jared is going to take those requirements and ask us some follow-up questions. So it says, thank you for providing those detailed specifications. Your requirements are quite specific and target high-end GPUs, which narrows down our options significantly. Okay, so it's good that it's telling us that. Based on your needs, we're likely looking at NVIDIA's data center GPUs, particularly from the A100 or H100 series. Let's refine our approach to find the best solution within your budget. Are you open to considering slightly used or refurbished GPUs if they meet all your technical requirements? So yes, let's say that. I'm open to considering used or refurbs if they meet the requirements. Let's do that. have you considered the infrastructure requirements for these high-end GPUs, such as power supply, cooling systems? Should we include those in our requirements? So nope, we don't need to include that. We don't need to include infrastructure and infrastructure requirements. I just want to find the GPUs, right? Okay. Given the high specifications and budget constraints, how many GPUs are you looking to acquire in total? This might affect bulk purchasing strategies. So let's just say I just want to acquire one GPU. Okay. Right. So we've answered another set of questions, and this is going to obviously refine the requirements. I think after this, we're going to put an end to the requirements gathering stage. So there are additional questions, and this process can go on as long as you want. Obviously within limit, because these large language models do have a fixed context. So, if it goes on for a long period of time, you will exceed the context, obviously, but I don't think any sensible task will exceed the context available to you from Claude 3.5. Let's move on to the next stage of the agent workflow. So this next stage will be ending the requirements gathering process, which is done by pressing /end. And then that's submitted to Jared. Jared knows to put an end to that requirements gathering process and pass our requirements on to the Meta expert. Now I'm going to bring up the backend here, and I'll have that slightly off screen, because once I submit this to Jared, what I would like to do is I'd like to show you how that looks in the backend. So I'm going to submit this, and now I'm going to bring the backend on screen, because it will illuminate for you that requirements gathering process, so you can really see how that works. So we've submitted that end to Jared. It's contacting the Anthropic API. And there we go. We have our requirements filled out. So remember that Kogor was blank at the beginning, and now we've got all of our requirements set out. So we have our budget, CUDA constraints. I'll just scroll up so you can get a view of that. So we've got our goal, CUDA constraints. We've got our budget of 5,000. We've got our memory constraint there. We're open to new, used, and refurbished. It says focus on the A100 and H100. So I think that's probably a mistake, because I think there are some GPUs out there that meet our criteria that aren't necessarily the A100s or H100s. But I could have said that if I wanted to. I could have told it to be more expansive. All right. So these requirements are passed on to the Meta expert. The Meta expert then derives first its chain of reasoning. So we have the goal here. We have the strategy. So notice the internet research summary is blank right now. The shopping list is also blank right now. We haven't visited the internet yet. Progress towards the goal is 0. We're not being asked to produce type 2 work yet. We have a strategy research available, NVIDIA A100s and H100s. And as I said before, I think we could have done this more expansive, but I didn't mention that in the goals. So that, I gather we're going to get back to some H100s or A100s. So it'll be interesting to see what we pull back. It says check pricing and availability, evaluate new, used, and refurbished options, compile a list of suitable GPUs. So that sounds like a solid strategy to me. We have an expertise here, and that's just generic expertise in high performance computing, hardware, etc. So it says an expert plan is required to effectively research and compare GPU options that meet the specific requirements. It also says under our controls, internet research is also necessary to gather current information on available GPUs, their specifications and pricing. A shopping list will be required to compare suitable GPU options and their prices. All right, so far this chain of reasoning all seems to make sense. It all seems to add up. And notice after that chain of reasoning, we have gone to the expert planner. So we've written a meta prompt for this expert planner. That, remember, the prompt is written by the meta expert. So we have a plan here, and you can pause it here to read this plan. But what's going to happen is this plan is going to be passed on to one of the known tool using agents, and you'll see that as I run through this backend. So you can see here, by the way, all of this writing in white, this is our state. This is the state graph that we capture in LangGraph. So you can see here the meta prompt is already filled in. I'll just highlight there so you can see that. Conversation history isn't filled yet because we haven't completed a cycle yet where we update the conversation history. The requirements gathering part is filled because we did the requirements gathering initially with the Jared Kogor agent. So that's what you see here. What you'll notice is as we start stepping through this agentic workflow, this state is going to grow because all of these parts are going to get filled in. So what you should expect to see next is the expert plan will get filled in, and then the research and shopping, and maybe even the writing, depending on what we're doing. And that will grow as I start scrolling down through this PowerShell. So let's move on. So you can see the no tool expert has been called here because we've written a prompt for the expert planner. So there's the expert. So let's see what plan we've come up with. So you can see here, we've actually derived an expert plan. You can read that here. This is our plan. And what that plan is going to be incorporated in our next chain of reasoning. I'll scroll down and you'll see where that comes in. There is a lot of debugging information in here, mainly outputting the state, actually. So, all right. So we're now on to the next iteration. And you can see, so we've invoked the meta agent 2 times at this point. So we're on to the next iteration. So those requirements, initial requirements stay the same. So the meta agent can keep track of those initial requirements. But now our chain of reasoning has been updated. And notice now there's a plan here. Notice the internet research is still empty and the shopping list is still empty. The progress towards the goal has shifted from 0 to 1 because we've now delivered the plan. We still have our strategy. So if you want, you can pause this here and have a read of that. I want to move this out of the way so you can see that. You can definitely pause this and have a read. But that plan is the plan that was delivered by the expert planner. The strategy is outlined as it was before. The expertise is outlined as it was before. So now notice the planning has been updated. So it says an expert plan has been generated and is now available in the plan section. This is a comprehensive plan that covers all aspects of sourcing suitable GPUs. So it acknowledges that we now have a plan, which is fantastic. Now we've moved on to internet research. So it says internet research is necessary to gather current information on GPUs, their specifications and pricing. We should proceed with this research based on our expert plan. Okay, great. And then it says a shopping list is required. Okay. So next, notice that we are now conducting expert internet research. And this is what the meta agent has created. Remember, we've created the chain of reasoning first and then asked to deliver the meta prompt from the meta expert, right? So this is what the meta expert has created. This is the task for our expert internet research. All right. So that will be passed on to the tool using agent. And notice the state is growing because we're filling out more aspects of this state. Let's keep going. You'll see where the tool using agent has been called. So the router is called the tool expert. Debug location. All this is saying is that we're searching in the United Kingdom. That's why it says GB. Let's keep going. Okay. So here's a significant step where it says generated search queries. These are the search queries that we're generating from the expert internet researcher. So these search queries are going to be across Google search. So the engine here is search, and here's our query. NVIDIA A100, H100 GPU specifications comparison for LLMs. And then we've got one for the shopping engine query, NVIDIA A100 GPU, 48 gigabytes plus memory price. And then we've got another one for the search, CUDA 12.4 compatibility, NVIDIA A100, H100 GPUs. And then we've got shopping again, refurbished NVIDIA H100 GPU for sale. And then we've got another query, NVIDIA A100 versus H100 performance benchmarks, LLM tasks, all right? So those seem like fairly comprehensive queries for the task at hand. We've now gone through to actually perform those searches. So you can see that we've connected to the Google Serper Dev API. And obviously the Serper Dev is the service I'm using to perform searches on Google via either the shopping or the standard search. You can see where we've connected and received results there. The 200 status gives you, tells you that we've managed to successfully connect to that API. And then we're doing a bunch of refining of those searches. And at the end, we get 2 data sources. So key thing to understand here is that these 2 data sources are not everything, because the way I've set this process up, this current state of Jared, we're only doing retrieval-augmented generation. So we're only doing RAG on the search engine sources. And the reason for that is because the shopping sources actually when you return this search engine results page for the shopping sources, they provide a good summary of the product and the price of the product, and also a link to the product page. And that's all we need for the shopping list. We don't need anything else. When it comes to using the pure search engine, sometimes we want to actually pull information from the page. So there might be some relevant things from the page that we need to understand, like whether something is CUDA capable or not. So you notice here, we've gone and visited the NVIDIA blog for CUDA Toolkit 12.4. So I gather from here, we're going to find out whether these GPUs are CUDA capable or not. So that's why we're only sourcing from 2 sources, even though we made 5 queries, okay? Also, there is a thing that the dupes, sometimes we do select the same source. So sometimes duplicates will be removed, which means that we've made 5 queries, but actually maybe we're just making 2 searches because we've removed some duplicates as well. All right. So we've done our intelligent chunking. So you can see where we're starting that intelligent chunking process for each source. And this is done with multi-processing. So this is all done in parallel. You can see where we started that LLM Sherpa for both of those parallel processes. Now, it does sometimes hang here. I have known it to hang here, and I think a lot of that depends on the specs of your machine. Hopefully it hasn't this time around, and we've managed to proceed. So it looks like we have managed to proceed. You can see we've prepared a total of 137 documents. Now we're going to start the indexing with face. So this is going to be the indexing and ranking. Indexing and similarity search with face. So you can see here where we're loading the model and we're performing that indexing and similarity search. We do it in batches. So there's 137 total documents. You can think of these as 137 chunks based on our websites that we visited. We've done some indexing and re-ranking and retrieved the top 40 documents. So indexing and similarity search, and just retrieved the top 40 documents of the 137. Then we're going to apply some re-ranking here. So the significance of the first level similarity search here is that it's kind of your quick and rough version. You do a basic similarity search with a bioencoder, and that gives you a basic order of, okay, these might be relevant to your query. These documents, so these top 40 documents are relevant to your query based on some ranking, based on a similarity metric that you have between your query and the encoded documents. The re-ranking is a bit more rigorous. So you use a cross-encoder to, once you have that top 40 documents, re-rank them again. And it's supposed to provide a more accurate view of what documents actually relate to your query because you're using a cross-encoder. So after using the cross-encoder and performing that re-ranking, you can see where we've done that. We take 60% of those top 40 documents. So we take the top 24 and we say that's the retrieve context that we want to give to the large language model, to the meta expert specifically, to produce our answers going forward. All right. That 60% is an arbitrary number. That's just a decision I made. If you visit the offline RAG tool, you'll see where I made that, and you can change that to whatever you like. So we've passed that phase now, and you can see the state is growing, and you can see a lot of context here from websites. So we're filling out the research now and the shopping list. And you'll see here, there's links dotted in here because that's from the websites we visited. The state has grown quite significantly. Let's continue on. We'll continue on. Okay. Now we're back, and remember the initial requirements that we got from the Jared agent don't change. But now we're being asked to produce type 2 work. So that means we're coming to the end of the set number of cycles that I've set for this agent to work, and we're being asked to produce type 2 work now. So we have our meta prompt. We have our chain of reasoning, and notice now the internet's research has been filled out. So the internet research has been filled out, and we have our sources here as well outlined. And also the shopping list has been filled out. And we have our sources for the shopping list outlined too. And let's have a look at our strategy. So we should be on step 5, make a final recommendation based on performance. We also have identified that we need to produce type 2 work now. So that's set to true. And if you take a look here, it says no additional internet research is required. as we have sufficient information to make a recommendation. It says we have a comprehensive shopping list and do not need additional items this time. So you can see how this chain of reasoning is helpful for guiding this agent to follow a strategy and return some results to us. Okay, so definitely pause and have a look at this chain of reasoning for yourself so you understand what's going on here. The important thing to know is that we've filled this out systematically by following this agent workflow, and then that's guided the next steps of the meta agent. So now we are producing our type 2 work, which is our final answer. And you can see we've produced that here. And instead of reading this on the PowerShell, what I'm going to do is I'm going to pull up the front end so we can read it on there. So here is our final answer delivered on the front end. So let's have a look at how well it's done to deliver a final answer. And look, Jared is by no means perfect. I don't expect this answer to be perfect, but the fact that we can guide agents to work through such a research task, which is fairly complex, to me is impressive. And it shows how far the technology has come along. So let's read the final answer together so you can see how well Jared has performed this task. So it says, based on the requirements and available options, here's the recommendation for high-end performance NVIDIA GPUs for running state-of-the-art large language models. So it says recommended, and we've got the PNY NVIDIA RTX A6000 48 gigabytes graphics card. Okay, so notice that's not an H100, and it falls within our budget because our budget was $5,000, right? So let's have a look at the justification. Memory requirement, RTX A6000 meets the minimum 48 gig of memory requirement. Fantastic. It says it's CUDA capable. And it says, as a recent NVIDIA professional GPU, it is compatible with CUDA 12.4 and above. It says, while not as powerful as the A100 or the H100, the RTX A6000 is still capable of running state-of-the-art LLMs with its 48 gigabytes of CDDR6 memory and 10,752 CUDA cores. Fantastic. The cost, obviously, is within the £5,000 budget. And it says it's available as a new product, ensuring reliability and warranty coverage. All right, so let's pull it up. Let's have a look. And there we go. As promised, we're directed straight to the shopping page for the GPU, and it seems like it's available. And if we wanted to buy that now, we could even get it by Friday, which is fantastic. All right. And there's a bunch of information here about the product. So that's worked well as a recommendation. The first recommendation definitely meets our criteria. And then it suggested alternative approaches. Alternative options. So we have the used NVIDIA Tesla A100. Let's take a look at that. So we have a used GPU here, and it says 8,000. So we have been directed to the page, which is great. We have the PNY NVIDIA A100. This is excellent performance, but significantly over budget and slightly below the 48 gig. So it says 40 gig. Let's pull that up. There's service unavailable. Okay. That is due to my internet connection, unfortunately. Let me try again. But the point is, we have managed to actually find the cheap GPU. And what's impressive about this to me is that initially it didn't know that we could go for the RTX A6000 because it was actually suggesting the A100 and the H100, but it's obviously managed to conduct some level of internet research to find that the RTX A6000 would be suitable based on our specifications. And we have some conclusion here. All right, so what I'm going to do is I'll save this down as an example task so you can review this for yourself. I would like to just demonstrate to you what would happen if we use this if we ask ChatGPT to complete the same task. Obviously, ChatGPT doesn't do that question and answer thing in the same way. So I'll just give it the requirements off the bat and ask it to do that same task and see what ChatGPT comes back with. And we can compare those results. So stay tuned for that. Great. So we've seen a demo of Jared. And some of you might be asking, okay, great. Why would I use Jared instead of just going ahead and using Perplexity or ChatGPT? So I'd like to benchmark how Jared performed on this task versus how, say, Perplexity or ChatGPT would perform on this task. I think the easiest way for me to do this would be to grab this Kogel. So let's grab all of the the requirements here. This explicitly expresses the requirements. I'll copy that. And then I'm going to pull up, we can start off with Perplexity. I'm just going to paste that logo in here. And I think that should be enough for Perplexity to understand what we're after here. And then I'm going to press enter and see what it comes back with. So it's kind of come back with a way for us to source high performance NVIDIA GPUs suitable for running state-of-the-art large language models. Not bad. We have our budget, and then it's come back with some recommendations. So it's recommending the A100 and the H100 GPUs. Let's see if we can pull that up. So it's just directed us to this blog from NVIDIA. So nothing that we can actually purchase, but it's useful information anyway. I'll close that. And it just seems to be more recommendations here. So I'm just going to hover over. So this is Reddit. That's a Reddit source. The performance as well. That's coming from the NVIDIA developer. But so far, it hasn't actually sourced anything for us or given us any prices. So obviously, this isn't the pro version of Perplexity. I'm not sure how well the pro version would perform. I don't pay for it, but you can already see that Jared offers some advantages over Perplexity in the sense that, we are connected to the Google shopping engine. It does take longer to render results, but that's because it is stepping through that active research phase and, doing local RAG and things of that nature that do take long and are computationally expensive. So what I'd say here is Perplexity is probably better if you want to do something broader, but Jared is maybe better for doing some deeper research. Okay, let's see how ChatGPT does with the same task. So with ChatGPT, I find that sometimes you have to explicitly tell it to use the internet. So I will tell it, use the internet. So I've given it those requirements. I'm saying use the internet. This is GPT 4.0, so this is the latest version. And we're searching the internet. So we quickly found 3 sites. Okay. All right. So it kind of seems like it isn't. All right. I think what might be confusing it is that step there. So step 5, where it says prepare the final summary for agent handover. So consolidate all the gathered requirements, ensure alignment with primary goal, verify completeness, organize requirements in a clear, concise format, prepare the final summary for agent handover. So maybe the strategy bit is confusing it. And that may be also a signal for me to remove this strategy bit to make this thing work more reliably. But I'll push it as it is. So, you guys can play around with it and let me know your feedback on that. But yeah, I think our requirements are quite clear here. It still hasn't really returned anything. We've got some key considerations here, and we've also got some links. We have links to the store. Okay, so we've got an NVIDIA A100 for 16K. That's good. Let's see what we have on Scan UK, scan.co.uk. So that's not really directed us to a specific GPU product, but I'm sure if we did search on this page, we would be able to find something. And let's redirect ourselves to Amazon. Amazon, I'm hopeful for. Okay, so it's just directed us to the Amazon homepage. So all in all, it hasn't really provided anything. I guess the advantage of ChatGPT and also the advantage of Perplexity right now is that because the state is persisted, I could always tell it to go back and find the actual GPUs if I wanted to. I could do that. I plan to build that capability into Jared too, so we have a persistent state so you can give feedback on the final results that are delivered to you from Jared, and it can work on that basis. That's on the feature roadmap. But yeah, that's one of the advantages of using a ChatGPT over something like Jared, or using Perplexity over something like Jared. But you can see there is some value that Jared does deliver to you in terms of deep research tasks that require, complex planning in a sense, and research to be able to complete those tasks. So you've seen what Jared can do. I want to spend the next few minutes just talking about some of the weaknesses of Jared, and I'd like to talk about some of the improvements or optimizations I think could be made on the project. So the first weakness I found is actually the reliability. So what I found is that, I've been able to get Jared to work for a variety of tasks But even so, sometimes the agent just falls over. So it might be due to a process that requires too much resources and it ends up hanging. It might also be due to Jared going rogue on the chain of reasoning or the planning process or the requirements gathering. This obviously happens more often with smaller, less capable models. I found the outputs for smaller, less capable models to be less reliable, but it also does happen with the larger, more capable models too. So even with something like Claude 3.5 Sonnet, sometimes you get outputs that aren't really in line with what you expect. Sometimes, for example, it just fails to go and search the internet and just delivers you something that it just pulled out of its memory. And obviously not useful if you're looking to source GPUs, for example. You want actual links to the page rather than just some friendly suggestions about how to source GPUs. So I have seen it do that. So that's the first thing on the reliability, and that's both in the form of actually getting the workflow to complete and not running out of, not taking too many resources and crashing out, and also actually delivering a final output that makes sense and is in line with what you want. The next thing there is the speed. So you'll notice that with something like Perplexity or with ChatGPT, they can search the web very quickly, although I think what they're doing is performing quite a superficial search. Jared is quite a bit slower than that. And where I have tried to add optimizations by doing parallel searches and multi-threading, there are some things that are just computationally expensive, and ultimately without a GPU, it's difficult to speed those things up. So those are the indexing and the similarity search that we do with the face in-memory vector store. If that could be done on a GPU, that could be sped up dramatically. So that's an area for optimization. And also the re-ranking as well. That could be sped up if we do that on a GPU. That's two areas for optimization. Addressing that weakness of latency with Jared. You do have to wait there for a while for it to get going. The other thing is the LLM Sherpa. So the LLM Sherpa tool is the tool that we're using. It's open source, locally hosted tool for document ingesting and smart chunking. For some unknown reason, there are some PDFs or documents or URLs that it ingests that it just doesn't work with for one reason or another. I don't know whether there's some missing information there or whether it's the format of the document. I think the types of PDFs that are just photos rather than so like a scan, it doesn't work too well with those. Now, there is an option for LLM Sherpa to use OCR. What they suggest on the repo is the OCR actually slows it down and doesn't really add that much value. So I haven't included that. So that might be an optimization. I am open to using a different type of document chunking method. I'm definitely open to that. Something that's a bit more efficient. I would trade off some level of accuracy for speed in terms of intelligent chunking. Although I think LLM Sherpa is a fantastic tool for intelligent chunking that you can run locally, so you don't have to make an API call out to some external service. So if you have any suggestions for that, that would be fantastic to hear. You can put it in the comments or make a suggestion on the GitHub repo. Now, there are a few other things here. Obviously, I've set Jared, for the examples I showed you, I set Jared to run a total number of 8 iterations. You can set Jared to run even longer running tasks. So you can set, in theory, you can set it to run as many iterations as you want. So it could go to 10, 100, 1,000 iterations. The issue you have is that context window is going to grow larger and larger. And sorry, the amount of tokens that you expect the meta agent to process or the meta expert to process is going to grow larger and larger with the number of iterations you have. And eventually you're going to hit the context window limits. Granted, it is a very large context window. So we're talking about, I think it's around 200K tokens or something for Claude 3.5 Sonnet. There are some models that have 1 million plus tokens, but ultimately you're going to pay more for a request like that. And I believe that Jared or any other LLM at the stage it is now is going to be more prone to making errors and delivering substandard outputs with much longer tokens. So I haven't tested it with an ultra long running task yet. Perhaps I will do that in another video, but it's something to bear in mind. In terms of the similarity search and indexing, perhaps using a smaller embedding model as well could help speed that bit up. So that's something you could try. You could try swapping out that embedding model. I think we're using an embedding model with 512 dimensions. Maybe if we use something smaller, it could speed up that similarity search a little bit. The prompt engineering is also a major area of optimization. I think there are probably some superfluous things within those prompts that could be stripped out to make, not only to make Jared more reliable, because I found as I've iteratively adjusted prompts and made them cleaner and more, improve the clarity of those prompts, I have managed to get some more reliable outputs. Or I have managed to, not reliable outputs, but I've actually managed to make Jared produce the outputs I want more reliably. I think there's a long way to go on the prompt engineering. That's an area of active development, and I will be iterating on that and improving it step by step. There have been some suggestions to transfer the prompt for the Claude server. So when we're using Claude, to transfer that prompt to XML rather than using Markdown. I have tried this and I don't find much of a difference. So I'm continuing to use Markdown for the prompts because I feel it's much easier to manage prompts in Markdown for me personally rather than using XML. I'm also seeking a way to monitor performance of Jared. So some kind of platform that I can use to actually monitor the performance of each of these agents in the Jared workflow. So I know there are platforms available from LangGraph. So there's a LangGraph platform for monitoring agents. There is something related, I think it's related to Langsmith. I haven't yet gotten access to it, but when I do, I'll probably do a video on that and should use Jared as an example to show you how to monitor the performance of agents. And that's just so that I can make my development process a bit easier. Because every time you do tweak something, this is such a complex system that it changes the behavior in ways that are perhaps unexpected. So yeah, a way of reliably monitoring the performance of agents in this workflow is going to be key to making Jared really performant as a research agent going forward. The videos I'll do next will be some more task-based videos. So I'm going to do some task-based videos to show you what types of tasks that Jared does well on. So far, I've gotten Jared to source me cheap Wagyu steak. I've gotten Jared to find me GPUs, as you've just seen. I've also gotten Jared to write me a newsletter. And all of those seem to be possible. I'd like to do some more challenging tasks. I'll be doing some videos coming up to show you how flexible Jared can be. So that was a long video today. If you enjoyed the content, give us a thumbs up. Feel free to give us your opinions in the comments section and subscribe to this channel for more AI engineering content. Thank you, and I'll see you on the next video.